Okay, so Dalton's law of partial pressures. If you usually in a whatever you're looking at, you have a mixture of gases. You don't just have one gas. And so the pressure of the gases mixed is going to be the sum of the individual pressures of the gas, which we call partial pressures. So the partial pressure of oxygen or the partial pressure of nitrogen, you add the two partial pressures if they're in that sample, and that would be your pressure of the gas, the whole thing. That's all that's really saying. So the total pressure, PT, is equal to the partial pressure of gas A plus the partial pressure of gas B. Now we're in the same system. R is the same, so our temperature will be the same, the volume will be the same because we're all in the same system. So each one of these pressures, I don't know. So if we have PV, okay. If I look at PV equals nRT, P is equal to nRT over V, right? The only thing that's changing is the number of moles of each gas. Everything else is staying constant. So if we add these two together, so if we're, now scribble this out. If this is for A and this is for B, so let's call this, I'll put a B here and I'll put an A here. For gas A and gas B, this is equal to NA plus NB times the RT over V, right? Which is how we get this right here. Because the only thing different is the number of moles. Their temperature and volume are the same. N is moles, number of moles. R is constant. Yep, R is the 0.0821. So that's how we get this equation right here, where if you have two, you can just use the number of moles, add the two number of moles, multiply by there. Or you could do them each separate. You could do this whole equation for that one and this one and add them together. You get the same answer. But when we take the number of moles of the gas 1, gas A, and divide it by the total number of moles in the gas mixture, whatever it is, then that is going to be called that's the mole fraction XA, so that's the mole fraction for A. So what we call this is XI, and I just stands for whichever gas it is. Okay, you can substitute any letter in there for there. You could substitute oxygen, nitrogen, whichever gas it is. So X, which is the mole fraction, is equal to the number of moles of that gas divided by the total number of moles. And that is our mole fraction. For that mixture, the whole mixture. Well, there's only hydrogen gas in that one. So if we had a mixture of nitrogen gas plus hydrogen gas plus oxygen gas plus carbon dioxide, when you add all four of those up, that would be your total number of moles. And then to get a mole fraction, you take just the number of hydrogen molecules, the number of moles, divide by the total, then do four of those for each of the mole fractions. And we can use that mole fraction to find the pressure, the partial pressure of that gas. So if you know the total pressure of the system, you can take that mole fraction times the total pressure of that system would give you the partial pressure of just that one gas. Does that make sense? Kind of? Questions? You would find that. But you would use that number times the total pressure to get the partial pressure of that gas. Oh, you could remember it all. This right here goes to figure out this, yes. That's
Figure out that?
yeah, this is how we get this. Matt, do you have a question? So here is a picture. If we have gas 1 plus gas 2 and we mix them, that's you take the pressure of gas 1 plus the pressure of gas 2, you get our total pressure. Yes.
Why isn't this easy?
It is really easy.
I like
Yes. So let's look at this problem. A mixture of gases contains 4.46 moles of neon, 0.74 moles of argon, and 2.15 moles of xenon. Calculate the partial pressures of the gases if the total pressure is 2 atm at a certain temperature. How are we going to do that?
You tell us.
You tell us.
We'll see if you're right.
So the total pressure is equal to the partial pressures added up. So we need to figure out the partial pressures. We can use our mole fraction to find our partial pressures. So if Pi is our partial pressure, that was equal to Xi, which is our mole fraction, times the total pressure, correct? So we need to find the mole fraction for each of them. What's the total number of moles? So what would be Xt? The total. Or no, let's not call it Xt. Let's call it Nt. Nt, the total number of moles. 7.35. Yep, you just add them all up. So now if I want to find the mole fraction for neon, what would that be? Yep. And what is that?
Where's the n in that first equation? I don't understand.
Mm-hmm. What's that mole fraction?
What's that x?
Xi. And that x is the mole fraction for whichever gas you're talking about.
And then why do you have to do that nt though? Is it nt the same thing as t? Pt?
That's the total number of moles.
Yeah, but what's pt?
Total pressure.
The t is total. The little subscript t. Yeah, I got that. But why is there an n and a p?
This is number of moles, and this is pressure.
So, but why do you have the pressure for the moles? Or are you using that type equation in that 4.46?
No, we haven't done anything with that top equation yet. This has no units because you're taking a mole divided by a mole. So now if we want to find the partial pressure of neon, we would take its mole fraction, which is 0.607 times 2.0. And so the partial pressure for neon is 2.1, and that is in ATM. Okay, what's the next one? Argon? XAR would be 0.74 divided by 7.35. 0.1? Okay. So if I want to know the partial pressure of argon, that would be 0.1 times 2.0 would give us 0.2 atm. Not too difficult, is it? Last one is we need the mole fraction for xenon. Would be 2.15 divided by 7.35. 0.3? 0.293? Okay, so then the partial pressure for xenon, 0.293 times 2.00. What was it? There we go. There's our partial pressures. One way you could check, add those three up. Does it equal 2? They should. There we go.
Okay. It won't get harder than this, right? Yeah, exactly. If it doesn't get harder, I'm fine. It won't be like, I'm good with words.
Oh, you weren't done?
No, it's fine.
Got.
I'm good with words.
Okay.
It's just sooner or later we'll become like ions and stuff. What was the final answer for partial xenon? What? Oh, this is looking yeah. The second one's exactly like the first.
Okay. Then how about you guys figure this one out?
Go for it. But it's going to be hard if you have nothing to refer back to.
That's why you have your notes to refer to.
But on the test, okay, fine. On the test, we're able to.
Are you guys cooled off back there yet? Okay. I can feel the cool air up here. Okay, I'll look for that one. Let me check these. Yep. Okay, so measure out this amount there, and then add it, get a volumetric flask of 500 milliliter one. No, 2 separate ones. Oops. Yeah. So what's your partial pressure of methane? Oh, you're not there yet. Okay.
I got
1.3. Do you guys all agree with 1.3 ATM?
or approximately 1.1.
What about ethane? Do you guys have ethane? Hold on. Okay. Oh. I thought I heard. Did someone say it? 0.06? Depends on how you rounded. Should be pretty close then. How about propane? Which one? 0.02 or 0.04? 0.02?
I kept the 8.766,
Mm-hmm.
so I'm off.
Oh, that would be fine.
Okay.
Do your best not to round as much as you can until the end, okay? That'd give you better numbers. Okay, what's the next one look like? Do we have another one? Yes. if we have halothane, non-flammable, non-explosive, and non-irritating gas that's commonly used as an inhalation anesthetic. So if we mix 15 grams of halothane vapor with 23.5 grams of oxygen gas, and the total pressure is 855 millimeters mercury, what's the partial pressure of each? How would we do this? Switch everything to moles, yep. So we have 15 grams. I'm just going to call that big H for halothane. I'll go HA. How about? There's no element HA.
How do we know what
CLF. It still has mass. Gas has mass.
It would be so. You have to have so much to get something to use.
Gas, how much it holds.
But you could put in yeah. Why is it grams and not milliliters?
It's a mass, not a volume. They have the mass of it. They don't.
Yeah, just
You can measure a mass of a gas. Which one? 79.9.
Is that worksheet tomorrow?
Okay,
Because you only have like 15 minutes or 20 minutes in class.
What are we doing? Where are we getting to today?
A worksheet.
Oh, I'm meaning notes. Where are we getting to? This is it. What's the molar mass? Oh, you're almost done. And so, how many moles is that?
312.84. 197.37.
Okay, I got way more than that.
There's two people with the same answer.
Alright, I think mine's closer of 312.
You have 300?
12, yeah.
12?
One extra zero on the
I,
voltage.
that's a little off.
Oh, that's why. I see.
Okay. So what is the...
Oh, now I got 532.
How many moles?
0.076.
Okay, 23.5 grams of O2. Remember, oxygen is O2. So our molar mass is 32, not 16. 7.8. Yep. Now what?
Yeah, 0.73.
0.73.
You gotta speak up.
Now we got to find the total number of moles. So NT, what would NT be? So then you would find mole fractions for each. Yep. So what is the mole fraction for halothane? Point 0.094.
Oh, you're holding it sideways.
Okay, and then what about O2? .906.
You already have one of these recorded? Or? Were you recording the whole time?
Not the beginning.
Hi, Lacey.
Not the beginning. So what's the partial pressure for halotane? This time we're in millimeters mercury, which is fine. We can leave it in millimeters mercury.
It is 80.37.
Come on. And how about for oxygen? Yep, multiply it by the total pressure. Should be like 780 millimeter. 774.63 millimeters mercury.
What is it?
Millimeters mercury. 0.63. 774.63.
You gonna throw something else again? Okay. That was just like
See.
So if we round different and we're close.
It'd be fine.
That's exactly the same thing. What I was doing.
Not quite.
Because anything closer to it,
Who's been
Ah.
writing all the dates and stuff up there?
I think Shayna's been taking care of it.
Hey Santa, have you been taking care of all the days? Have you been taking care of the countdown?
So sometimes, or a lot of times when we look at gases and we create gases, we collect them over oxygen. So what happens is that we create a gas in a solution, and then the gas would bubble up and be filled to the top, and we'd collect it. When you do that, you get some water vapor in it. So we're going to use the same partial pressure laws that we had, but it's kind of a specific one where we have partial pressure of oxygen plus the partial pressure of water vapor, and this water vapor depends on the temperature, and so you'll look at a chart and actually get that. Would give you the total pressure. But it'd still be the same thing. We're going to be doing it the same way. Yeah, we'll walk through one of them. It's going to be very similar. I'll give you those for.
worksheet have this too?
Yeah. So let's do the problem. No, you're not done. Oh. Can I switch it? No.
So like on one, if they give you, what if they gave you temperature? What do you do with that? It says a 2-point-liter flask at 15 degrees Celsius. What, you just don't do anything. It's just extra info.
Those two are just
Yeah, it's like the.
Mhm.
Oh, awesome.
Can I switch it now?
You may.
So this is what, if we're making a gas here, a gas in order to be condensed, it has to be run through water, colder water, and it would it'd come up through the water, and then this gas would fill this container and the water would be pushed down. And so you can get a bottle full of gas. This gas would be whatever gas you're trying to get plus water vapor, so you have to just take that into account. So if we look at this problem, where oxygen gas is generated by the decomposition of potassium chlorate, the volume of oxygen collected is at 24 degrees Celsius and atmospheric pressure of 762 millimeters mercury, and that is at 128 milliliters. Calculate the mass in grams of oxygen obtained. And it tells us the pressure of the water vapor at 24 degrees Celsius is 22.4 millimeters mercury. So if we want to look at, if our total pressure then, so PT, is equal to 762 millimeters mercury. And we're trying to get just oxygen gas, so we have oxygen gas plus water vapor. What would be the partial pressure of just oxygen? If we know that water vapor is 22.4 millimeters mercury, how would we figure that out? Just subtract them. Yep, just subtract them. So what would that be? 740.6? 739.6. So that is our pressure of oxygen, and now we can use that pressure to calculate the mass using our values. So I would go ahead and find moles, find N. So we have, what would it, PV equals nRT. And we want to find N, so we'd have PV over RT equals N. So what's our pressure? Right, use the 739.6. Oh, but we're using R, so what units do we have to be in? We have to be in ATM, so we got to change that to ATM. Yep, 760. So 0.97. So our pressure is 0.97. Our volume, 0.128. We have to be in liters. Yep, whenever we use R, we have to be in liters. R is 0.0821. And then T is, so what is N? You have to change this to Kelvin. Temperature.
I was like, what the heck?
What'd you get for N? 0.005? You guys agree? Okay. Then we just got to change that into grams. So we would multiply by 0.005 moles. And we're in oxygen, so 1 mole is 32 grams, right? So our final answer would be 0.16? 0.16 grams. I guess we should put O2. O2. Very good. Tomorrow we'll start with that second problem.
Yes.
So
Monday?
You can't get it done to win.
See how much you can get.